Hello, my name is Michael Reeves, and I'm a cybersecurity researcher at Sandia National Laboratories, and today I will be presenting a security study covering 59 CVEs from 11 different runtimes and the corresponding defense motivated by the results of the security study. This work is an extension of my research during my master's degree at Purdue University. So before we get started, we have to talk about what a container is. A container is an isolated process with operations constrained by kernel isolation mechanisms and kernel security mechanisms. Kernel isolation mechanisms affect what a container can see. These consist of C groups and namespaces. C groups set limits on system resources, while in namespaces, each resource namespace is given a unique copy of system resources. So for example, in the PID namespace, only all processes in the same PID namespace can see other processes in that same namespace. This enables isolating container processes from each other and the host. In addition to container isolation mechanisms, we also have kernel security mechanisms. These affect what a container can do. These consist of Linux security modules, seccomp, and Linux capabilities. Linux security modules enable mandatory access control on the Linux operating system. Seccomp acts as a firewall for system calls, while Linux capabilities break up the all-encompassing root user into 38 fine-grained permissions. So now that we've talked about what containers are, we have to talk about why adversaries want to control container hosts. This can happen for one of three reasons, the most prevalent being where an adversary compromises the container host to spawn cryptocurrency miners in a cryptojacking campaign. They could also want to conduct corporate espionage or exfiltrate customer data by compromising the container host. So now that we've talked about what containers are and why adversaries want to attack container hosts, we have to talk about how they actually accomplish this task. And so this is done through what's called a container escape, where the attacker is able to execute code on the host from inside the isolated container by exploiting an exposed vulnerability. These container escapes can happen for one of three reasons, the first being a misconfiguration vulnerability, where the adversary exploits a poorly secured container. The second being a kernel bug, where the adversary exploits a kernel vulnerability to escape. And finally, the third being a runtime vulnerability, where the adversary attacks a vulnerability within the container runtime itself. Now, all these vulnerabilities can occur because a container is not a VM, and it's not running on emulated hardware, while it's actually a process on the host. Because these vulnerabilities occur, they can enable escape, and in the escape, the attacker is able to execute code on the host. And so, during our literature review, we found 5 works that apply to this research. The first was from Lin et al., where they study container escapes which exploit kernel vulnerabilities. The second was from Anton, which is a previous thesis that investigated container escapes from all 3 categories, but only examined 4 CVEs. The third was Martin et al., where they studied container escapes exploiting Docker container misconfiguration vulnerabilities. The fourth was Flausic et al., where they did a comparison between container runtime technology features, but they did not discuss any vulnerabilities. And finally, the fifth was Elodie et al., where they conducted a vulnerability risk assessment by comparing discovered CVEs to actively used exploits. And so, from our literature review, we found that no work can analyze container runtime vulnerabilities. So to fill in the missing gap, we conducted a security study to understand the impact of these vulnerabilities on the container host. From our initial data collection, we found 11 runtimes and their corresponding 59 container runtime CVEs. And because these CVE descriptions lacked key details to analyze the impact on the container host, we focused only on CVEs with proof-of-concept exploits. We found that 28 CVEs had a publicly available proof-of-concept exploit. Next, we split these container runtime CVEs into a 7-class taxonomy based on the cause of the CVE and impact of the exploit. This analysis revealed that 46% of CVEs had a proof-of-concept leading to container escapes. These 9 proof-of-concepts covered 13 container runtime CVEs. After additional investigation over our 9 proof-of-concept exploits, we determined the underlying cause of the container escapes exploiting container runtimes was a host component leaked into the container. And so finally, to determine if these escapes could have been prevented, we applied a user namespace defense to prevent exploitation of root privileges on the host. And so as a result, 7 of the 9 exploits were prevented. So now, we're going to talk about our security study. In order to conduct our security study, we first built a threat model, where the system was a Linux server running containers, as microservices or as a container as a service provider. We assume that the adversary had code execution inside the container image, either through remote code execution vulnerability present in the container, buying the service as a container as a service provider, or through the administrator downloading a malicious image and executing it. The goal of the adversary, regardless, is to control the container host by exploiting the vulnerability accessible inside the container. For our trusted computing base, we assumed that the container profile configuration, the Linux kernel, and server hardware were all secure. This forced the adversary to escape the container utilizing a container runtime vulnerability. So next, let's look at an example container escape exploit. The example here is 2019-5736, and it's a runC vulnerability that occurs mainly in 3 steps. In the first step, the adversary maps the entry point of the container to /proc/self/exe and forces it to load a custom shared object file with a new function that overwrites the executable which loads it. Next, the symlink executes in the container on startup, and /proc/self/exe executes the host container runtime by using the host file descriptor that's referenced in /proc/self/exe. So the host container runtime is running in the container, and the shared object overwrites the container runtime binary on the host. And so finally, in the third step, the new containers that are executed are actually executed with the overwritten binary on the host, and it executes the evil functionality input by the adversary. So this happens for one of 2 reasons. In the first, the adversary executes a host binary inside the container and thus can control its shared object. And 2, where the adversary can overwrite the binary because it has access to a host file descriptor inside the container. So next, let's go over our data collection, which occurred in 4 steps. In the first step, from Google searches and literature review, we built a list of popular runtimes. This list can be seen in the key for the bar chart on the right. In step 2, we utilized the NVD Tools open source command line utility to parse the NIST National Vulnerability Database. We gave it the input of 11 runtimes and got the output of 59 corresponding CVEs. This bar chart on the right breaks down the vulnerabilities by container runtime based on their CVSS score, their common vulnerability scoring system. The CVSS score defines the severity of the vulnerability, with the higher being the more severe. As you can see, 40 of the vulnerabilities are higher critical severity. And so we can see that container runtime vulnerabilities are high severity exploits. In step 3, we filtered the CVEs, removing denial of service vulnerabilities as they were out of scope, and focusing on CVEs with proof of concept exploits. As we said before, we had to focus on proof of concept exploits because it enabled comparing the cause and the impact of the vulnerability, and the CVE explanations were not satisfactory. They were mainly missing step-by-step technical analysis and the exact privileges gained by the adversary. And so finally, in step 4, because we were looking at only proof of concepts, we had to get links to all of these. And the National Vulnerability Database only had 12 proof of concepts available. So we supplemented the search with GitHub and Google queries for proof of concept exploits that were not available in the DB. In total, between the National Vulnerability Database and GitHub and Google, we found 28 proof of concept exploits. In the graph on the right, we list out the severity of the container runtime CVEs with proof of concept exploits. And so next, we're going to talk about our taxonomy. In order to build our taxonomy, we first had to build an analyzer framework. We could have chosen from a low level, which would have involved a binary comparison, but not all proof of concept URLs provided proof of concept source code. We could have chosen a high level framework, which could have used something like MITRE ATT&CK framework, which would have allowed comparing all proof of concepts, but important technical commands that were required for an exploit would not have been included in the analysis, since the high-level framework would have produced only categorical results. So we decided on a middle ground framework that would break down the exploit into high-level adversary commands called steps, where steps capture the missing details from the high-level framework, but do not require compiled exploits like in a low-level framework. And so an example of this is on the right, with a natural language description of the adversary steps for CVE 2019-5736. This is a more complicated version of my 3-step explanation. And so now we can actually see the taxonomy with exploits distributed by the cause of the CVE and the impact of the exploit on the host. And on the right, we can see the 7 categories separated by the number of CVEs in each category. We put these categories into 2 camps, non-escape and escape. The non-escape exploits were associated with the vulnerabilities that do not result in adversary-controlled code execution on the host, while the escape exploits are associated with the vulnerabilities that enable the adversary to gain control code execution on the host. All of the non-escapes are the non-blue categories on the left, while the escapes are all in blue. And so we can see the container to host escape category takes up 46% of all the CVEs, and so we decided to further analyze these and determine the exact causes for why they occur. And so each escape exploit occurs because of an unintended host component that's exposed in the container. And this host component exposure occurs from 3 issues. In the first, because of a mishandled file descriptor. And the exposure occurs from a mishandled file descriptor when a file descriptor remains accessible inside the container via the /proc file system, which gives the adversary read-write access to the host file system. In the second case, for runtime component missing access control. And in this issue, the exposure occurs because the adversary gains access to a host runtime component that failed to implement fine-grained access control. And so finally, in the third issue, for adversary-controlled host code execution, in this issue, the exposure occurs because a host binary executes in the context of the container, which enables the adversary to manipulate an execution through either a malicious shared object or a malicious symlink. And so finally, let's talk about the namespace defense. And so given that 48% of CVEs lead to escape exploits, and 58% of containers still run as the default root user, we decided to apply the user namespace to each container runtime with an escape exploit to determine if these vulnerabilities would still be exploitable. And so let's explain how the user namespace works in greater depth. By default, a container runs as the same user that initializes it. Thus, the user's ID is the same in the container and the host. So in this example, when a container running as the root user executes the make node syscall to create a reference to the host file system, the syscall succeeds if the user in the container is root. However, the regular user will fail since they do not have the proper capability make node, while the root does. However, once we apply the user namespace defense, this changes things. In the top box, the container running as root can access the host block device. However, under the user namespace, the container running as root in the bottom cannot. When container UIDs are checked for permissions on the host, they are transformed into the real UID at evaluation time. So container A without a user namespace evaluates to root when permissions on the host are checked, while with a user namespace, the UID of the container A is actually a non-root user on the host, so the container fails the permission check. And so, when we apply this defense to the CVE 2019-5736, the exploit will fail to overwrite the host binary. In step 1, when the host attempts to start a new container, the malicious code in the new runtime binary is executed. But, in step 2, it is prevented from overwriting the runtime binary as its permission check to overwrite the host container runtime fails on the host. As before, a container root user does not map to the host root user, and so the permission check fails. And since 7 of the 9 exploits are prevented for similar reasons, this defense paradigm becomes a powerful tool to prevent the adversary from breaking out, if the adversary gains execution in the container. Thus, the user namespace defense is simple and effective at preventing a majority of runtime escapes. However, 2 of the exploits to continue to succeed after applying the defense. And so this points out a limitation of our defense, where the user namespace defense cannot stop exploits that take advantage of runtime utilities which execute as root, but depend on container-controlled objects. And so as an example of this, one of the 2 successful exploits, CVE 2019-19921, utilizes a time of check, time of use vulnerability in runc's volume mount operation. This talk-to vulnerability occurs before the container is fully initialized, so the user namespace defense cannot prevent the attack. And so, we propose the same solution as the runc developers, which requires a fix to the software architecture of runc. In order to do this, runc is modified to mount directories using the file descriptor of the specified mount, rather than a string of the mounted file path. In this way, the entire race condition is avoided, because the file descriptor will always point to the correct file path, and the adversary cannot race runc to trick it into mounting malicious paths. And so, in conclusion, we have presented 3 novel contributions. The first one being a security study covering 11 runtimes and their 59 CVEs. The second, a 7-class taxonomy over the CVEs with publicly available proof-of-concept exploits, which reveals the main cause of container escapes is a host component linked into the container. And 3, a defense that applies the user namespace to prevent exploitation of root privileges on the host. And it prevents 7 of the 9 exploits studied. And so, overall, our paper presents the first thorough study of container runtime vulnerabilities and demonstrates that applying user namespaces to containers may effectively prevent container escapes. And so now, I'm happy to take questions.